Alright, here we are with the beaglebone set up to work on the robot with power on the motors and everything. What we can do now is we can try and transfer our program that we were running previously on our computer to the beaglebone, and then try and see if we can control the motor, one motor with it, like we did before, but with the beaglebone now. So here we are on the computer, and let's connect to the beaglebone. SSH BBBW. We're on. We have a folder here called projects, and in here we have the WheelHandler project. I moved it in here, and you can see the code is here. I did disable parts of the UI because showing the UI of the WheelHandler with a moving scope and everything is just too much to do for X11 or Wi-Fi. So I had to disable it for it to work. The build folder is out here. And I already built the WheelHandler for ARM on the beaglebone. And let's try and run it. Oh, so when you SSH into a computer, in order to show any UI from the remote computer, you have to SSH in with a argument. We have to provide -x to the SSH, and then we can run GUI programs as if they're running on this machine. So here we go, WheelHandler. So this is WheelHandler now running on the beaglebone and transmitting its display onto this desktop. Let's try and set the target speed. And as you can see, the motor is running. If I try to stop it, it's going to fight me because now the beaglebone is regulating the speed of the motor. It's not actually showing anything on the graph. I had to disable the graph, and I also had to disable the speed bar up here, because otherwise the regulator just didn't get enough CPU time to do its work. This is all we need in order to make our robot. Since the beaglebone is a little bit slow to compile both for the Arduino and for itself, we can develop all that we want to do here on this machine. We'll connect that to the Arduino temporarily while we're developing it, and then once we have something that works, we'll switch to the beaglebone, build it there, and then run it from there. Alright, so let's get started programming the Arduino. The gyro sensors, accelerometer, and magnetometer has a library for Arduino on GitHub. That is what I'm gonna use. It has it sets up all the boilerplate code, all the configuration of the sensor, and it makes it quite easy to interface with it. So I'm gonna copy that into our project. As you can see, now we have it here. The IC that we're using is the MP9250, and these are the InventSense libraries that do most of the work that is not related to the specific IC. Anyway, let's get started. In order to connect to the gyro or the this library, we will make a new C++ header and C++ file that we'll call sensors.hpp, and we'll make a CPP file as well, sensors CPP. And the sensors, of course, needs to include the header. The CPP file needs to include the header file, like that. And then in the header file, we need to do if defines. If not defined, let's call it sensors. HPP. I don't know what happened there. Sensors HPP. Then we're gonna define sensors HPP, and then we're gonna have an indif. Then we're gonna include Arduino to be able to do any kind of Arduino stuff in these libraries. Then we are gonna make a function to set up our sensor. Set up IMU, and we're gonna make a function to get sensor data, and we're gonna make a struct with our sensor data, and we're gonna send it in as a reference. Let's make a struct sensor data, and in the sensor data we're basically gonna use that to send our data to the computer. It's gonna have a float with the accelerometer x value, and let's just copy this. So x, y, and z. Then we're gonna have with gyro x, y, and z. And then we'll also do the speed pulses here. Speed, that's gonna be u and 8t speed pulses. So that's all our sensor data that we will gather and send to the computer. Right. All right. Let's actually implement some stuff. So here we're gonna actually implement our bodies of our two functions like that. Let's see if this builds. It builds and compiles. Great. This first part of setting up the IMU, you can look at that in the documentation. In order to do it, we need to actually include the libraries we need. We need wire.h. This is part of Arduino to communicate over serial on the serial ports or the serial pins. And then we're going to actually import our MPU 9250. This is the library we imported from GitHub. And in the documentation, it tells us to do wire.begin wire set clock. They tell us to do 400,000 baud. That's a lot, but that's fine with me. imu.config, and here you send in the wire pointer, and you send in the MPU protocol for communicating I2C addresses like that. And then we can actually begin the IMU. So if not imu.begin, then something really serious has happened that went wrong, and we have to handle this. If so, serial.print line. Let's just for now, let's just write a text message error initializing IMU, And then we can also do a test. We have to do a test or config some serial data rate stuff. Config srd 90. I don't know what this means actually. It's just in documentation. I should probably look it up. And if this fails, we are going to do serial print line error configuring srd. All right. And if everything goes well, we'll just write serial print line IMU initialized. Yeah. So we could try and run this and see if the IMU actually initializes. We should be able to see that in the serial monitor. I don't know why I just closed that. That was not intended. Let's open it again. Here we are. Let's try and build it and send it to... Oh, we have a bug. It says here, IMU was not declared in the scope. And that is because I didn't declare the IMU. Actually, I have to do some more boilerplate stuff here. I have to set the MPU address. And that's gonna be hex 68. And then we're gonna do a BFS MPU. And we're gonna... So this is our actual IMU object that we're declaring right here. And yeah, I forgot that. Let's try and build this. We still have problems. Oh yeah, the IMU for some reason has capital letters in the functions. And so we need that. And now it complains that what does it say? Invalid user. I did something wrong here. Set up IMU census line 16. Oh, it's here. Yes, that's definitely wrong. All right, and I accidentally pressed compile and send. And let's see if that actually, let's just clear that and let's do it again. And we don't seem to be getting anything. And that's because we didn't call it in the setup function here in our INO. We need to include in our INO project file our actual sensors HPP file, and then we need to call the setup IMU function. Here we go. Done uploading. IMU initialized. There you go. It should work. We get to here. IMU initialized. Great. All right. So here in sensor data, we need to actually detect if we if there's any data ready for us from the IMU, and we need to first see if we can read something. So we can do if IMU read, and then if it doesn't read, then we'll just return. And let's return false, because then we didn't get any data, which means we need to change the return type to bool. All right, then we need to test if there's any new data for us. IMU new IMU data, and If there's no new data, then we return false. All right, and then we can return true. If we have these things, now we just need to actually set the data. Let's set the acceleration part of our sensor data. Let's just see. Why didn't the IntelliSense detect that? That's kind of strange. Okay. imu.accel xmp s2. So this is the acceleration in meters per second squared. And let's see if that builds. It doesn't. Ambiguous declaration of get sensor data. Yes, this is why it complained. We forgot to set the return type here. And let's see if it works now. Yes. Maybe you also have no. For some reason the IntelliSense or whatever, the auto completion doesn't work in Arduino Studio right now. Anyway, let's continue this. Just copy this and do it for the X, Y, and Z coordinate. X, Y, Z. And let's do that for the gyro as well. imu.gyro x in radians per second. And let's do that as well for Y and Z. And then let's set the speed pulses. Let's just set that to 0 for now. And let's see if we get some data from the actual IMU. So that seemed to work. Let's try and actually call it. So in here, our loop, we will have to get some sensor data here. And then down here, we'll say if get sensor data, we'll send in our sensor data there. Then let's just write print line. Let's just write IMU data gathered. For now, let's just see what happens here. And let's run it. It's uploading. IMU initialized, and it says IMU get data gathered. All right, let's see if we can actually get some of the data from our Arduino to show in the serial monitor. Let's do acceleration X like that. No, this won't work, will it? Let's see what the easiest way to convert our number to a string. Let's just do string number st.x. Oh, now it works. Okay. And let's do just a print like that, and then a print line where we put in our data. Print line in. So this should show us some data. Let's just clear this. Yeah, seems like we get some data there. Let me move the robot a little bit and see if we get some different data. Seems like we do. All right, awesome. So now we have data that we get from the IMU, and let's actually communicate that back to our computer. So it's going to be a little bit more complex right now. We can't just send. We also want to be able to send some errors from the Arduino. We want to do some more stuff, so we need to implement a little bit of a protocol, a data transmission protocol to handle the different kinds of data from the Arduino. And so let's do that. Let's actually make a serial com header file and a serial com cpp file. Serial com.cpp, like that. And here we need to include the header, serial com app, like that. And here in our serial com HPP file, we're gonna do the if defines. If not defined, serial com HPP, copy that, then define serial com and if. And here we're gonna set up serial communication, void setup serial, and let's make some functions. Void send error and void send sensor data. Here we're gonna do some a message with error data or a string, and here we're gonna do our sensor data, like that. And so we also wanna define some stuff to for our protocol. So let's define a byte to start our data, and I like to do this with byte value of 160, and then have an end byte. Define end byte 85. These two bytes are the inverse of each other, and they're not 0 or 1. So this one is like that, and this one is like that. So this has the benefit that the start byte and the end byte is not 0 or full, and they're the complete opposite of each other. The chances that you'll get these two bytes at the correct place when you have an error is less, I think. So that's why I do it. Hit define. We need to also do a byte where we send what kind of message we are sending. So let's do an error data byte, error type byte, and let's do a sensor data type byte. That's kind of crazy. And these will just be normal byte values. That's okay, I think. Let's actually implement our functions. We've got to actually import our Arduino library here. We need that. All right, let's make some function bodies. There we go. Set up serial. We're gonna move our serial stuff here. Put it in here, and I think that's it for now. boink. And let's just delete it from here. We don't need that now. But we do need to set up serial. And we need to include serial HPP there. And let's see if that builds. Not built. Send sensor data. Yeah, we are trying to send our sensor data here. We could do a forward declaration of sensor data, but I don't want to do that because I need the size of sensor data to be available. It should be, but let's just do it here. All right, it still complains. Error variable field declared void. Error variable field sensor data declared void. Sensor data was not declared in this scope. SD was not declared in this scope. Interesting. Sensor data is right here. See. Oh, I should do sensors.hpp here. Let's see if that works. Yes, it builds. Right. Let's actually do some protocoling here. Serial dot write start byte serial dot write error type byte. No, it's decided that auto completion doesn't work. Annoying. And let's actually do let's actually write the message and let's end it. And write and type int byte. Let's see if that works. It works. I don't know why it doesn't do the auto completion for some reason, even though I have saved this file. Okay. All right, that's fine. Let's also implement the sensor data. It's going to be a lot like the send error function, and instead it's going to be sensor data. I forgot there was a long one here. Let's just copy that. Sensor data type byte. And here we can't just send the sensor data in the write function because it doesn't have a way to it doesn't have a way the write doesn't have an overload for our sensor data. So we're just gonna add a message here. I'm gonna declare it a char array, and then we're gonna cast our sensor data into a char array, and then we're gonna send that. However, we need to give it the size because it is not null terminated like the string is. So here we need to say size of sensor data, I think. Let's see if that works. Invalid cast, yes, we need to convert it into a pointer. There you go. This actually worked. Awesome. So let's actually try and see if we can get this to work. All this new serial communication stuff. So in here in the sensor CPP file, we'll include our serial hpp so that we can send data from in here. And we can do that. If we get an error here, we're gonna do send error, and then we're just gonna copy that from here. Okay, that seemed to work. Oh, and let's just copy that over here. We actually don't have a function to write when it's good, so let's just make one. Let's call it void send info const jar message, and let's make a new define here. Info the type byte. Info type byte s3. All right. And let's just copy this one. And info type byte and byte. Let's see if that builds. It builds. Let's actually use it then. Send info. Yes. And right, let's see if this actually works. Maybe we should just stop printing this right now just to see if we actually get some data here. Boink. Let's go in the serial monitor, clear this out, and see what happens. And we initialized, and we get the data right there. Awesome. Is that zero terminated? We'll see that. If it is not zero terminated, we might need to put a 0 on there so that we actually know when the strings end. All right, good. So here we could, instead of doing this, we could actually just do a send sensor data, and like that. All right, that's kind of cool. Let's also make some more files. Let's make a file to control our motor, HPP, and let's make one motor CPP. The CPP file needs to include the HPP file. There we go. Then here on the, we need to do the if defines. Then define and if. So here we'll make a function called setup motor. Motors. We have 2 motors, and we might also want a function to read the pulses from our motor. Void get motor speed pulses. And that should probably contain the uint at. And yes, what else? We need to set the motor speed as well, or force you void set motor speed intensity, and this should probably get it 8G left and uint 8T right. We also need a way to set the direction because yeah. So we basically have a byte value that defines the intensity of the output of the motor using the pulse width modulation, but the motor controller also has a pin that defines if it's going forward or backward. So, and these are related, so I'm just gonna let's just let's have it together. So dear, let's call it a bool, and let's call it forward, I guess, left, or direction left, and bool direction right. Yeah, that's pretty good names, I think. And let's make these functions. Let's make some actual bodies. Like that. Like that. And let's see if it builds. It does not build. Arduino 8T does not name a type. So here the problem is probably that we just didn't remember to include Arduino here. Yes. That's it. So let's actually call it here. So set up motors, and we actually need to include that here. Include motor HPP. And so the pin modes are actually part of the motors. But we need to make this a little bit so let's make a we need to have some way of abstracting our motors, and let's do that with struct. Let's let's just call it motor, and our motor is gonna have some member variables to specify the pins. So we're gonna have a pin for the PWM pin. Then we're gonna have a pin that defines the direction. And then we're gonna have a pin that defines the pulses. Speed. My naming convention has been a little bit off here. Let's just do like consistently. Speed. Pulse pin. Speed pulse pin. Let's just call it speed pin. Like that. And then we want to get the motor to actually accumulate the speed pulses. And then we'll do that. Speed pulse value. So we need to detect whether it has changed on each motor. So let's do a bool here. Speed pulse value. And let's set, yes. Right. All right, so let's make an actual init functions here. So we need to specify these values here. Yes, like that. Let's just call it PVM pin. Let's call it PP, DP, and SP for PVM pin, direction pin, and speed pin, like that. And then let's actually set it. PVM pin equals to PP, dir pin equal to DP, speed pin equal to SP. Then we need to set the pin mode. So pin mode, this is going to be the actual pins that we're setting here. So PVM pin is going to be set to output. The direction pin is a little bit complex in that the Arduino, this motor controller, detects the direction by setting it low. So it is a the input pin needs to be floating if it's not set, and it needs to be low if it is set. And that makes it a little bit complex in that we need to change the output mode, the pin mode, depending on the direction. And anyway, so for now we're just gonna set the output, the dir pin, to input. This will make it floating, which means the direction pin is not set. Alright, so let's do pin mode, speed pin, and that is an input as well. And yes, and let's just set the speed pulse value to false for now. All right, good. All right, let's do a set force function here on our motor. And oh, we could actually do the yes. So we could do the level and direction here. So intensity, and then we're gonna do the direction here. Yeah, so we're gonna that we're actually gonna return, get the motors, and then we're gonna set it directly on the motor object. That's how we can do it. All right, so first we need to handle the direction. If direction else, so if the direction is true, then we set pin mode to output. Direction pin output, and then we're actually gonna digital write to direction pin low. So we're gonna set the output to low, and we're gonna set the output. And if it's not true, then we're gonna set it to input, which will make it floating, and that will make the motor go in the other direction. All right, then we're actually gonna set the PWM value, PWM pin, and intensity. There you go. So that should set the motor. Right. Let's make a function to read the speed pin, the pulse pin. Read speed pulse, and yes. So first we need to store the pulse value in a variable and then compare it with the speed pulse value we have in here. And if they're different, then it's going to return true, I guess. Yes, void bool. So bool so speed pulse value equals this yes, let's actually just take the old value and store it here, and then we're gonna set the speed pulse value equal to digital read and speed pulse pin like that, and return speed pulse value is different from speed pulse value. Yes, this should, so now it should return true if it has changed. So in here we're gonna do motor left and motor right, and then here instead of motors we're gonna actually init, so left init, and let's just initialize it here. So the pins we're using we have set up right now on the robot is, for the left motor is 5, 8, and 9, and for the right motor it's 6, 7, and 10. I wrote that down. like that. That should init the motors. Should we just do a send data? Let's do that. Include serial com, send info, motors initialized, like that. Get motor speed pulses. Maybe we should rename this. Maybe we should just return the sensor data here, or we should set the sensor data here and like that, and then call this read speed. Oh, that's kind of a cool name actually. Read speed pulses. Read speed pulses. All right, and then here we're gonna do SD dot speed. I can't remember now what I called this. Speed pulses. And let's just plus to it. If the left motor read speed pulse, did we call that? So if it's true, then we add 1, otherwise 0. And let's do it with the right motor as well. Should we separate them or should we have them together? That's a good question. Maybe that might be an idea in separating them. Maybe not. Let's just have them together for now. We're just gonna combine the two motors, and because we don't have directions anyway on the motors, there might actually be some information in the fact that if one motor's running and the other one is not, then it means that the robot is rotating. And that could be useful data maybe, but let's do that if it becomes a problem. Yes. All right, set motor intensity. Let's just do it here. Left. Set force. Why did I call it force? I should call it set intensity. Let's do that. Set intensity. I call it that everywhere else, so let's just do that here as well. And it takes so now I decided not to get the auto completion to work. That's annoying. First intensity, then direction. All right, so left, dear, left, right, oh, and then right, and I do right, dear, right. Okay, let's build it and see what happens. Do we get some problems here? Read speed pulse. All right, so I changed this function. Let's just change this accordingly, and let's see if it builds. It still has some problems. Member function in HPP error SPV was not declared in the scope, line 32. SPV? Oh, SPV. All right. And then it says variable fields read speed pulse declared void. Oh. We need to, in order to get the sensor data here, we need to import the sensor data header file here. include sensor. Okay. Then we have error request member set intensity in left, which is a non-class type. Huh? So this is in the CPP file. So here it says request from member set intensity in left, which is non-class type. Oh, the naming. We have to write something here that can distinguish the names. Right, intensity. All right, let's see if that helps. All right, this is compiling and building. Let's actually upload it and see what happens. Everything seems to work, and it's actually getting some data. It says I'm initialized again, and then it says motors initialized. Great. Maybe we should also have one that says serial initialized. Now we have it. Why not just also do that here? Serial initialized. I mean, there's no point really. Because if the serial isn't initialized, then it wouldn't begin even. But just to get some consistency, it's always nice. All right. All right, so we actually still need to do some work here. We need to set the motor intensity, and we need to actually read the speed. So let's do the speed first here in the sensor data. Let's do that before we return with a false. So in get sensor data, let's just do here. We probably need our motors. Include motor. Dot. Why are we complaining? What? Oh, that worked. Auto completion just stopped working. Great. All right. Read speed pulses or okay. Why are there two? Read speed pulses. Oh, it's on the yeah, I see. Okay. Sensors read speed pulses, and it takes this one. So now it'll send in the data, and then it will accumulate the speed pulses in the sensor data. So when we send the sensor data, we need to reset the speed pulse value in the sensor data. Let's just do that. So in serial com here, let's just make sure, let's not do it here. Let's do it up here. So here we'll say send sensor data SD speed pulses equals to 0. This makes sure that every time we send it, we will accumulate new speed pulses. All right. On a sum. And this still builds, right? So right now, this should be good. So the serial event, this function needs to be here in the INO file, but whatever's in here could be in the serial com files. So let's just make a function called handle serial event, and let's just put that in here. void handle serial event. I don't know if it actually needs anything. Let's just keep it like this. Serial.com. Let's put it in the bottom here. Give it a body. And then let's copy this in here. See if it builds. It builds. So here we actually have to begin parsing our communication from our computer, and we can't just take any byte and just write it to the motor anymore. We need to actually implement the protocol here as well. Let's just do this. Let's outcomment this, and let's actually just read our data. Let's just copy this. So read a byte, and then we'll parse it. Parse byte, data byte. Let's call it data byte. And let's make an actual function for that. Void parse. And it should take a uint ht data byte. Yes, that should work. And let's make a switch statement. And we should probably have some way of knowing our state in our protocol here, or in our parser. So let's call it parser state and let's make an actual parser state struct here, an enumerate, sorry, parser state. So our parser can be in a state of start and data reading and end, I guess. So read a start byte, then we're in the start state. Then we read a type byte, and then we're in the data state. Yes. All right, so let's do the switch on the state. Let's actually just set the state here. State, it's gonna need a semicolon there. State is equal to parser state end. Does this work? Serial.com line 41. Oh, yes. That works. That actually works. Great. Case parser state and so if we're at the end state and we read a start byte, data byte equal to data start byte, then we go into start state equals parser state start. And we probably need a way to count how much data we've gotten. So let's just say data counter equals 0. And let's actually make an integer here, data counter, like that. Yes. Yes. And let's break this. Parser state. So if we start, then we're ready to read what kind of type of data we have. So if data byte equals so we probably need some more types here, because here we need to receive the motor values, the motors, what should we call it? Define motor motor control type. That's maybe wrong. Motor state. Yeah, maybe motor state is not bad. Motor, let's call it motor regulation type. Regulation type byte. And let's call that 4. All right, so motor, and for some reason, IntelliSense has decided to not work on me again. So I have to copy this. All right. Then, yes, we need to, if we send more than one kind of data type to the Arduino, we need to actually know what kind of data we are receiving. So let's just call that type uint 8t data current data parser type data type parser data type. That's a good name. Let's just set it to 0 to begin with. All right. So here, parser data type. Actually, we're just gonna set that equal to the data byte, because that is gonna be the same thing. There's no reason to test that. And let's break out of it. And the state should now be, start. That should be state. State equal to data parser state data. I think it is. I forgot. Start data end. Yes. So we set the data type, and now here in parser state data, we actually need to handle that data, and let's do that in a function. Parse data data byte. Let's actually call that up here. Void parse data. And we are going to receive the same thing here. And yeah, our little protocol is taking shape. Error expected, semicolon before state. Okay. Line 55. That's right. And it builds, and it should run. But it doesn't really do anything. It doesn't read any data. So the question is, what kind of data are we gonna get from our computer? Instead of just a byte, until now we've just received a byte every time with the speed of the motor, but we actually also need we also need the directions. So yeah. So for now, we know that our data is basically always going to be just the motor regulation. We don't have any other. So we're not actually really going to use the parser data type yet. We're just storing it for now. It's always going to be the motor regulation data. But it's ready if we want to send other kind of data to the Arduino. So let's just do a switch here. And let's just, why does it do this? Data counter. And case. So the first data we're gonna get in our regulation data is gonna be the direction. Yes. And a byte contains 8 bits, so we can just do a bit shifting operation to get and just set the bits in the byte, the first 2 bits in the byte, to determine whether the motors are going left and right. So the first byte is going to contain directions for both motors. Yes. All right. So okay, so our data counter, is that going to be 1? No, that's going to be 0, right? Yes, because up here we set the data counter to 0, then we can read the type, and then we go in here. So that's going to be 0. And yes, let's just break that for now, just to be sure. So we need to store this data somewhere. I'm just going to store it here for now. Bool, dear, right, false, bool, dear, left, false. And let's actually also just store the intensities, U and HT, left intensity, and U and HT, right intensity. All right, so here now we need to do some bit shifting operations. Dear right equals, all right, so we take the data byte and we'll end it with a mask. Data byte, and let's do that the first byte. So right is going to be the first byte, and then that should do. Actually, let's, so okay, so here a byte is actually, a boolean is actually a byte, and if I just set it equal to this, I'm not really sure. Depends on the compiler how it detects true or false on a value. So let's just do true, false, like that. And let's do that with the same thing with the left. Yes, so now if data byte value number 2 is true, bit number 2 is true, and then this will become true, otherwise false. If data byte bit 1 is true, then this will be false, and it doesn't matter what the other ones are. Yeah, that should work. Case. We need to actually increment the data counter. So, yes, so let's do that after here, data counter plus plus. So case 1, the next byte is gonna be our write motor. Why is it doing this? Come on, break. It's jumping around in the editor all the time. I don't know why it's doing that. Super annoying. So let's just store the write intensity first. And that's just gonna be the byte, I guess, data byte. And if case is 2, left intensity data byte, and if we have count to number 3, then we're done. Let's just do default here. In case we have some lost packet loss, this should eventually get to if data byte is end byte. Now it works. Then yes, and yes, end byte. All right, and the data counter needs to be 3. So let's just handle. All right, so if it's the end byte, then our state is gonna be parser state end. If data counter is 3, then set motor intensity so intensity left, direction left, right, direction right. Oh, I kind of swapped it here. That's a little bit stupid. Well, so left intensity DL left, right intensity DL right. Yes. That should work. So in case anything goes wrong in the data transmission, it and we kind of skip a byte and we don't get to the correct end byte, then we'll go into the default and we'll just skip all the bytes that aren't end bytes, and then we'll get in here and change the state to end. So if some data is lost or a byte is wrong, then we'll kind of just skip it. If it's all right, then the data counter should be 3, and it will set the motor intensity. And so this is like a success criteria on the protocol. And yeah, so I think this should work. Yes. Awesome. If this works the first time, then I'm gonna be amazed. No. Set motor intensity was not declared in the scope. Okay, we need to actually import the motor here. Include motor.hpp. Let's see if that now builds. It does build. It does run. Amazing. Alright, so I think we have everything that we need now in the motor end and the serial communication end and the sensor end. I think the Arduino is almost ready. Here in the INO file, the actual Arduino project file, we're still having some of the old code related to the data transmission. So we had this counter here that would count up a bunch of speed pulses, and then it would, once it got all the speed pulses from the motor, or once it got 1,000 of them, 1,000 reads, it would send the data to the computer. But now I think we're actually going to use the IMU data available. It depends, like if we get into issues where this data available rate doesn't match with the speed in a proper way, then maybe we won't use this, and we'll do another way to do the speed pulses. But I think this might work. All we just need to do is register the data rate that we get the speed pulses in, and then we do what we did before. Now we just get speed pulses for 2 wheels, so we have to remember that and divide it by 2. Anything else here I think is actually not really needed. So let's just outcomment this. This data transmission counter, and all this stuff is now moved into the motor struct. Don't need that. All this stuff is not really needed anymore. So and let's just move this up in the top. It's nice to have our variables up in the top. I like that. We also could do that here in our motor CPP. Was it not here? The serial. Yes. Let's just move this up here with the other variables. See if it builds. It does not build. Speed pin val. Oh, digital. Yeah, we don't need this anymore either. Let's just remove that, and let's remove that boiler stuff. All right. Yeah. So now our INO file, our Arduino project file, is actually much simpler than it was before. We moved most of our code into these into these files that where they kind of segmented into the kind of stuff that we do. So the sensors have the sensor reading, the serial communication does the serial communication, and the motor handles the motors. And then the event loop, or the loop, will just kind of call this from here. Yeah, so we get the data here, we send the data here, we handle the serial events here. This should work, I think. Let's build it, and it's running. Let's just clear this thing, and we're actually getting some data in the serial monitor. Although it's binary data, so it's not very readable in the serial monitor. Let's just close that for now, and let's jump into the computer and implement our protocol there, and read and set some values to our robot, and see if we can read some speeds, read some gyro information, and so on. All right, so on the computer side, we need to do a lot of new stuff. The beaglebone is so to say a headless computer. It doesn't have any graphics, it doesn't have a display. So we will have to change our project into a console project instead of a widget project. We'll also need to implement the protocol that we have from our Arduino messages, both sending and receiving. And yeah, so I think we'll let the WheelHandler stay where it is, and we'll make a new project, a new console project for this. So, alright, so here we are. I now have two projects in my Qt Creator. I have a Gyrobot SBC project for the single board computer, and I have the WheelHandler. And I'm just gonna copy some stuff over. We don't need the main window, we don't need any of the GUI, but we do need the serial handler. So let's see, can we copy this here? I'm not really sure if we can. Probably not. So I'll just add that. I'll just copy the files actually. So up here we can now say add existing files, and Gyrobot SBC, here we have serial handler. So now we should get it up here. Let's see, yes. So now we have a serial handler, and we have a main function. That's good, that's good. Let's just see if we can get the serial handler working first. So let's just make a serial handler object, new serial handler, and let's see if I want to end it like that. All right, let's see if it builds. Serial port, no such file direction. Yes, so we still need to be, like in the WheelHandler project, we have added serial port to the modules up here. We have to do the same thing here. Qt plus equals serial port. Let's try that. Okay, let's try again. Q serial port, no such file or directory. Oh, I did. Let's see, maybe this works now. No matching function serial. Okay, so now we get another error. All right, so serial handler has no matching. Okay, so the constructor is not right. So let's see. Our serial handler needs a parent. I think we should be able to give the core application as the parent. Let's try that. And let's see if it accepts that. It did accept that. And it built. All right. let's actually try and start the serial handler and see if we get anything functional out of it. Start serial. And the port is going to be /dev/t2acm0. And let's see if that builds. It builds. Let's see if it runs. Serial port opened. I think it works. Alright. However, the question is, do we get anything useful in the serial? So right now we're just kind of getting the data here, and let's see, where is the... So here we have the onRead did a timeout. We're doing some stuff here on the frequency. Let's actually see if we actually get some data here. Let's just try and print it out, see what happens. Q info, and let's just do the whole thing here. Let's just see what happens. Oh, I have two running. There you go. Oh, yes, it works. Serial initialized, and we're getting all sorts of stuff here. All right, I think we might actually be on the road to something. So let's actually make our serial handler handle our data. So let's just copy our code from our Arduino in here, and let's also we'll use the same state here. We can that'll work fine. And we should probably have so our serial handler should have a data counter. So actually we already have a data counter here. Maybe we can reuse that. That might work. We might still want a way to calculate the frequency. So let's make a new one and call it data frequency counter. Like that. And let's go and so all this stuff is basically, let's outcomment this. Wait, this is good. The data frequency counter, we should really only do this. Let's see, mutex clear. So all this, let's outcomment that. Like that, and we should be ready to read and parse our data. And we'll do it similarly to how we do it on the Arduino. So here we'll just copy this actually, and we won't do the QInfo thing now. Let's just parse our data here. So instead of emitting wheel data here, we're gonna parse. Let's just copy that. Let's just make a function here called parse. And now we'll be doing the same thing as we're doing on the Arduino. And let's make a serial handler parse function that takes a data byte here, and let's parse this the same way we do it on the Arduino. We might even copy it. Yeah. Let's just copy this. So, all right. So this is the wrong one. I should have taken this one. Yes, the state. And we'll make it a member variable. So we'll call it m.state, m_state. And so we probably need to move the parse state out in the CPP file here. Parse state. And then we'll make a parser state m_state, and we'll set it equal to parser state and as a default. Yes. All right, and down here we can now actually use that here. So m.state should be here. It already recognizes the start byte, the parser state, the data byte is here. Here it's going to be m_state. Same here. And yeah, I think that should be parser data type. So we should also add this. Let's add that up here. That is just going to be a u and 8t for now, and we'll call it m_parser data type, and do the same thing here. Data counter, that should be m_data counter, and we will rename this one like that. All right, and then we should have a function called parse data, and let's just, yeah, yes, yeah. All right, void WheelHandler parse data u and 8t data byte, and let's just that was capital P, we don't want that, so let's just add the private declaration for this function, and let's add a private declaration for this function. All right, and now this should work. Parse data, yes, it is now recognized as a function. It became blue. And then up here we need to receive whatever data we get, and in this case we actually need the parser data type in order to figure out how to parse the data, because we have the error data and we have the info data and we have the sensor values data coming from the Arduino. So we need to figure that out. But we're gonna do mostly the same thing as we're doing on the Arduino. So here we're gonna say case. So we're gonna use the m underscore data counter here, and then case 0 is gonna broke. So in case 0, this is where we're gonna get actually we probably we get the parser data type here on the start. So probably we should switch on the parser data type instead, like this. And then maybe we should add an enumerate to reflect the parser data type. We could do that. Yes. No. Let's just use, because we already have them as defines. So we're just gonna use it like this. Let's do the info data first. Info data type byte. And then we'll make a function. Serial handler. Parse info. Data byte. Could have just copied this. Parse info. So we need to add a declaration here, private declaration. And now we should be able to say parse info here. Come on. Yes, data byte. And break out of that. Oh, we already have that. In fact, we can. Why don't we just part? Let's use the same function. Let's just pass that through here. And so we need to specify here whether that it is a, whether it's whether it's an error or, let's just, for now, let's just do it like this. Let's not really concern us. Let's not make any difference as to if it's an error or an info. Let's just do it like this. And then now we can copy the actual parsing of the bytes with the data counter. Break m underscore data counter. All right, so the first we're basically just gonna use a buffer to store the messages. So let's make an actual byte array for messages, message data. And here we're just gonna pass it into our message data, data byte, like that. Should work. So we should probably also, when we receive the mess parser data byte, so if the data counter is 0, we need to clear the message data. And then we should add the data byte there. And if the data byte is 0, because we're going to make it the 0 terminated, then we need to change the state. So if data byte is 0, then state is gonna be parser state end, no? Oh, so do we have a protocol problem here? So we need some way now to register that the string is actually done. Because the next byte is gonna be the end byte. And so what do we do to yes, so I don't think there's another way to handle this than to add an actual variable where we store message ended. Bool message ended false. All right. I don't think there's another way we can do this actually. So if data byte is 0, then message ended equals true. Yes, if so here we need to do if message ended else we want to add it to the data. All right, so now we are also adding the 0 termination byte to the message data. If the message is ended, we want the state to change if data byte is equal to end byte. State and parser state and all right, so if message ended, it'll always go in here. Yes. And here we will increment the data counter plus like that. Like we do on the Arduino. And so I think this should work for the info. We come in here, the case will be 0 by default. We clear the message data, yada yada yada. And if our data has ended, we change the state, but we should also emit a signal. We should have a signal for the serial handler for messages. Do we have? We actually already have an error. We should probably have an info as well. Info const q string that. So right now we can't really tell the difference between errors and info. So let's just do that. So we need to store that somehow. Oh, but we have it because we're storing the parse data type here. So we actually don't need to do anything more. We can actually just do it here somewhere. Where is the... So here, if type is info message type byte, then we emit info q string, and we take the message data here like that. And else we can emit an error. Oh, why did that not work? Error like that. All right. Let's see if it builds. It actually did not build. No implicit boolcast. Data byte. Const is private with this context. So the byte array operator to do the adding data doesn't accept. Might be because we are using the wrong operator. Let's just try this one instead. Yes, that's it. All right. Data counter was not declared in the scope. Did you mean data counter? Yes, I think it is what I meant. Yes. And oh, data frequency counter. We want to use that one instead here. All right, all right, all right. It builds. Awesome. Let's actually see if we get some information from our Arduino. And let's see if we can actually print it out. So let's make class. Let's call it Gyrobot AI. So here we have Gyrobot AI, and on Gyrobot AI we're gonna have a public slot on info, and it's gonna take a q string info, and let's actually make in the class, let's make a function here, and let's actually just write that out now to the debug, the console, just to see that we're getting something. And we need to add include qdebug in order for this to work. All right, like that. And then we need to connect it. We need to create an actual Gyrobot AI. Gyrobot AI guy. And let's add the header file. New Gyrobot AI. And it's gonna take a parent. Let's just do A here. Doesn't it take a parent? No. Funky. Let's just do that manually then. And that's a Q object parent, like that. All right, so that should work, I think. Then we need to, let's just see if it compiles. No, it does not. QObject macro does not inherit from QObject. Right. I added that. QObject. Now it doesn't accept the application. Oh, it needs to be a pointer. Like that. Let's see if it builds. Now it builds. All right, let's connect. Oh, we can't do that. So our problem here is that we can't connect. Yeah, we can. We can say Q object connect. The sender is going to be the serial handler, and the signal is going to be info, and the receiver is going to be the guy, and the slot is going to be on info, like that. Let's see if it builds. It should build. It did, and let's say it runs. Serial port opened. Nothing else. Nothing else. That's not good. So why don't we get our parser is apparently not working at all. That's pretty terrible. On reader data timeout. Parse read data I. It should get in here, I think. So let's just try and log if we are. If we're not getting in here, then something else is completely wrong. Let's try that. Okay, it is parsing. Interesting. So if and so let's see if we ever get into a start byte here. Let's just do this first, and see if we ever get in there, and then let's do this to ever see if we get into start, and let's see if that works. We do get in there, and oh, interesting. Now it actually wrote something. Serial initialized, gobble gobble gobble, IMU initialized, gobble gobble gobble, modus initialized. So we actually get something. That's interesting. And we're not. Okay. So I wonder, it seems like we got it all in one go. And that could be because we never got a zero string, a 0 point. But why didn't we get a 0? And why did we then ever get an end? That's interesting. So on the Arduino side, we might need to change our code so that we actually forcibly send a 0 byte when we where did it go? So here when we're sending, we might need to write a 0 into the serial here, just to make sure that we get that, because it might not send the 0. Yes. really depends on how the write function works here. Let's oh, I can't write to it if the C++ program on the computer side has it open already. So now I compiled, I uploaded, it worked. So let's try it again here on the. All right. Now we got serial ini. All right, so I'm an idiot. I forgot to switch from Arduino Studio to Qt Creator while I was working on this last piece of code. Unfortunately, so in the last piece of code I added on info, on error, on sensor data to the Gyrobot AI, and I think I actually already had that. And the uncensored data, I received the uncensored data here, and I just try to print out acceleration value of the z-axis. Then that's so I didn't do much here. The most of the stuff I did was in the serial handler where I parse the sensor data. And so here in the parse data function, I added a case for the sensor data type. I added a function called parse sensor data, and up here in the parse sensor data, I added a sensor data struct similar to the one from the Arduino. In here in the header, I added a sensor data member variable to the serial handler. I then typecast it into a uint8t byte array. Then I make sure that the data we get is not larger than the size of the sensor data, and so I'm not writing into any memory that's not sensor data memory. And then if the memory is larger though, then I check for the int byte. If the int byte is there, then I emit sensor data. And otherwise, I write the data byte to the sensor to the sensor data struct. And yeah, so that's basically what I did in the 20 minutes of video that I'm missing. So anyway, if we run this now, you will see that we get serial port open, serial initialized, and sometimes Arduino for some reason never gets any further than that. Maybe we have an error and we don't see it. Let's just connect the error as well, just to make sure. Error and error like that. Let's see if we actually get some errors. Maybe it works this time. Initialized. Oh, this time it worked. Well, maybe next time we'll see if something happens. Anyway, now we get some sensor data from our Arduino. We get this is the z-axis data. So right now it is pointing upwards. If I reorient the robot, you can see we get some other data from the robot. And yeah. Did it stop? Why did it stop? It might have overloaded the buffer, the output buffer. All right, so that is good. That is good. Let's stop writing this to the output, so we don't overflow our output console output with senseless accelerometer data. Alright guys, it's been actual 2 hours now of live coding and we had to stop. It's been good, and we have data now from the Arduino. The actual gyro and accelerometer data is now being transferred to the computer, and next time we will look into actually rerouting that data into our PID regulator, and we'll see if we can make our robot balance on two wheels. Until next time, bye bye.